Hello, this lecture will cover pages 249 through 254 of my lecture notes, so please print those pages out and have them in front of you as I present this lecture on Chapter 9b, Instantaneous Power and Average Power. We're going to start getting into the detail now of steady state power analysis on page 249, and in this chapter we're going to discuss 5 topics. Instantaneous power with sinusoidal inputs, average power with sinusoidal inputs, and maximum power transfer with sinusoidal inputs. We're also going to discuss RMS, or effective values, and power factor. In this particular lecture, we're just going to cover the first 2 topics, instantaneous power and average power, with a few examples. First of all, let's look at instantaneous power. Just as the name implies, it's instantaneous with respect to time, time variant with respect to time, so it's a small p. And if we use our convention, where the time variant voltage is equal to Vmax times the cosine of omega t plus some phase associated with the voltage, and we use the current, which is Imax times the cosine of omega t plus some phase angle associated with the current, then the power law says that the instantaneous power is equal to the instantaneous voltage times the instantaneous current. And I just move these down with the substitution, and I get this expression here in watts. Well, just for a minute, forget about this phi1 and phi2. I'm just looking at this expression here with this substitution. Using a trig identity we probably haven't used in quite a while, you know that the cosine of one angle times the cosine of another angle is equal to 1/2 the quantity, the cosine of the difference between the 2 angles plus the cosine of the sum of the 2 angles. And that's really what we have up here. If you take a look, we have the cosine of an angle, which we're going to call phi1, that's omega t plus phi v. And we have times the cosine of another angle, which we're going to call phi2, which is omega t plus phi I. This Vmax and this Imax, they're constants that just come out front when we use this identity. You'll see that in this step here. So now we're just going to use this trig identity, substituting in this quantity for phi1 and this quantity here for phi2. Very carefully, just a little bit of algebra, we get the instantaneous power equation, which is equal to Vmax times Imax divided by 2 times the cosine of the difference between the angles, which is phi v minus phi I, which is simply the impedance angle, if you will, plus Vmax times Imax divided by 2 times the cosine of 2 omega t plus the sum of the 2 angles. I want you to take a look at that equation because it has 2 distinct parts to it. It has a constant value. Take a look at this first front end here. It doesn't have any omega in it. It's a constant once you know the phase angle between the voltage and the current. And then it has a time varying portion to it that's sinusoidal at twice the frequency of either waveform up above. See the 2 omega? That just comes from this identity. So there's an expression. Now there's an example in the book that shows us the result of instantaneous power. But keep in mind, instantaneous power has a constant part. It's always going to be there. And it has a time variant part. So if you take a look at example in the book, it's example 9.1. I made a page reference, but this is the actual circuit here. We have V T and we have some impedance Z, and we want to look at the power, the instantaneous power in that impedance. If the voltage forcing this circuit is 4 times the cosine of omega t plus 60 degrees, and the impedance is equal to 2 at an angle of 30 degrees, that 30 degrees is the impedance angle. That 30 degrees is the impedance angle. We want to find the instantaneous power in the load and plot all values on the same graph. So if you take a look, we know the current is equal to Vmax. We converted this all over here to the frequency domain from the time domain. You can follow along in your notes. There's the voltage, phasor voltage, divided by the phasor impedance. I get the phasor current at 2 at an angle of 30. I can come down and I can go ahead and show that current. So the power, the instantaneous power, is simply equal to 4 times the cosine of 30 plus the cosine of 2 omega t plus 90 using the equation on the previous page. I skipped a step there, but I think you could go back and look at that and just make the substitution. The power in that circuit under the forcing function of 4 cosine of omega t plus 60 degrees and the impedance being 2 at an angle of 30 is equal to 3.46 watts, that's a constant, plus 4 times the cosine of 2 omega t plus 90 degrees in watts. There's a time variant at twice the frequency, and there's an average component. Instantaneously, a closer look at this, just in mentioning at impedance, we know that's the polar form of the impedance that we found up above. You get back to rectangular form, it's 1.73 plus J1, so that means it has a real part of the resistors in that box up above right here is 1.73 ohms, and the inductive reactance is 1 ohm, which would be shown as a plus J1 if you're looking at it in terms of a vector quantity. So what I'd like you to do is take a look at this example problem 9.1, and what I did was I plotted that. And I want you to notice something here. The one curve right here represents the voltage, and you can see where it has a maximum value here. The other curve represents the current, and you can see where it has a maximum value. So what the author did is he plotted the voltage and he plotted the current. And if you multiply these graphically point by point, multiply this times this, and you see you get these different points here. And this is the power. This is actually the power waveform. I want you to notice something. 0 watts is right in the middle here. That's 0 watts. It's this center point. It's this point right here. Notice that waveform is offset in this direction. That overall power is offset in that direction. That's the constant value that's always going to be there. And then notice the instantaneous power at particular points goes above that and below that average value at twice the frequency. You can see that this is twice the frequency of either one of the currents or the voltage. And you could go ahead and look at that real close, and you could pick off where we're getting this peak point here and where we're getting the peak point on the current and the voltage from the previous time domain equations or phasor domain representation we had there. So that's an example in the book I thought was pretty informative. Let's look at average power now. Average power is a lot more useful. Average power is also called the true power. So depending on a textbook, some books call it average power, some books call it true power. Same thing. Well, I could just give you equations for it, but I think I want you to know where these equations come from in a minute. So what I'm going to do is we're going to take a look at the average of anything, okay, is you take a look over a certain period of time and you divide by that time. I mean, that's what average is. You sum everything over a certain period of time and you divide by that time. So here, we're taking this instantaneous power and we're going to integrate it from 0 to t. That's going to give us the total sum, or the area. And I divide it by the period. Same period I'm using in the integration here. All I'm doing is taking the instantaneous power from the previous 2 pages ago, and I'm putting it in here. And I'm just going to integrate that from 0 to t, 1 over to t. Now, if you take a close look at this right here, okay, this Vmax times Imax divided by 2, okay, times this cosine of phi v minus phi I that comes from that identity that we used. This is just coming from that identity that we used. So I went from here to here using that identity. That's a constant again. Remember, we called that a constant. Well, you know that constant's just going to come outside of the integration. You don't integrate the constant. So I'm going to call it just k. I'm just going to call this whole value here k, and I'm going to bring it down here. And this value here, when you integrate this over a period, it goes to 0. If you integrate this over a period, it has omega in it, it just goes to 0. Think of that. There's area positive, there's area negative. They cancel out. So this whole thing goes to 0. So all you end up doing is integrating this constant, 1 over t times k t, evaluated from 0 to t. Well, if you go through that, you end up just with the constant. The average power is simply whatever that constant was. Most textbooks just go from average power or true power right to this equation right here, right to this equation here. But this is how you end up with the average power is simply equal to that constant value we got in the instantaneous power. The average power is equal to Vmax times Imax divided by 2 times the cosine of the phase angle between the voltage and the current, which we know is just the impedance angle. That's the impedance angle is just equal to Vv minus Vi. Also, it can be shown here, if you take a look, there's one equation for the average power or the true power. You can use that if you have the impedance angle. If you know Vmax, you know Imax. Well, do you see here that what you can do, and I showed you on the page here, is you can take this 2 here, and you can divide it by, you can separate it into square root of 2 times the square root of 2. And you put Vmax divided by the square root of 2 times Imax divided by the square root of 2 times the cosine of the phase angle. Well, that's the RMS value. That's the effective value. Vmax divided by the square root of 2 is 0.707. Same thing with Imax divided by the square root of 2. You get a 0.707 in the numerator. Go ahead and invert the square root of 2. You'll see that. So basically, the power equation you could use for average or true power is this equation here. Or you can use that the average power or the true power is equal to VRMS times IRMS, if you know the RMS values. I'm getting it from this. Times the cosine of the angle, of the impedance angle. Also, it can be shown that the average power of the true power is equal to Vmax squared over 2 times the impedance magnitude times the cosine of the angle. You can use this formula, you can use this formula, or you can use this formula. They're all the same thing. I'm just making substitutions. So, on page 252, for a purely resistive current, for a purely resistive circuit, V and I are in phase. So Vv minus Vi is equal to 0. So the impedance angle is 0. So the average or true power is always going to be equal to Vmax times Imax divided by 2 times the cosine of 0. The cosine of 0 is 1. So there's the equation you'll see in the textbook. Average power is equal to Vmax times Imax divided by 2. That's that constant power. If you go back here and look at this, that's this front end constant power. Look right there. That's all it is in the instantaneous power. That's what you have along. That's the offset that's always there. This is the time variant. If you're interested in instantaneous points, you have to take that into consideration. But if you're not concerned with instantaneous points, which you are not a lot of time, you can just use this. Remember, the average power is equal to the true power. And like I said before, you can divide this 2 into the square root of 2 times the square root of 2, and you can come up with this equation, which I also give you. The average power is equal to the true power is equal to VRMS times IRMS. If you know the RMS values, you just multiply them together. And that's in watts. No angle. Why isn't there any angle? Because they're in phase, and the cosine of 0 is 1. For a purely reactive circuit, or it can be for a purely inductive reactive or capacitive reactor circuit, the angle is either 90 degrees or minus 90 degrees. That's the phase angle. And the cosine of plus 90 or the cosine of minus 90 is 0. So the average power, remember I told you this before, the average power of a purely reactive load, purely reactive is the key word there. If it's all capacitive reactance or if it's all inductive reactance, it's 0 watts. There's no power dissipated. No average power dissipated, because it takes power on the positive cycle and it returns it in the negative cycle, either through collapsing the electric field or collapsing the magnetic field. We talked about that. So if I ever give you a problem where you're talking strictly a circuit that's purely reactive, the average power or the true power is always 0 watts. Has to have resistance in it to have dissipation. What I showed you here is I have a control system that I've worked on in the past, and I have to control a lot of water in this commercial building I have. And I went out and I bought a PVC solenoid valve, a 2-inch PVC valve. Cost me $187, but it's rated at 24 volts AC at 5 watts. Now I know that's RMS and I know that's true power. Okay? So I wanted to find out if I could use a small little transformer that I bought. You've seen these little transformers that's similar to the ones that you plug into a router or a switch that plugs into the wall and it has a little plug at the end that you plug into these things. Well, I wanted to just cut that and resplice it right into the electrical wires on this guy to see if I can control this water flow. A lot of water flowing through there, 2-inch diameter. So the specifications on this solenoid valve was 24 volts AC, okay, at 5 watts. So this was my analysis here, and I actually did this. The voltage RMS is 24 volts AC of the solenoid. The average power was 5 watts. So I went to find the current. I just used one of those equations that I just gave you. I used that equation. I come down. I found the RMS current of 0.21 amperes. That's 210 milliamps. So the adapter that I ended up buying is 120 volt AC to 24 volt AC. You had to be careful. They have 124 volts AC to 12 volt DC and 24 volt DC, but this was AC. This solenoid valve was in the specifications, I bought it as 24 volt AC. So I went and bought an adapter, 120 volt to 24 volt AC at 500 milliamps. And it will have no trouble operating that solenoid valve. The voltages is what have to be the same. But you can have, I mean, if you're spending more money, if I could have got an adapter that was 1 amp, 1,000 milliamps, or 2 amps, which is 2,000 milliamps, which they had them rated, but I'd be wasting money. That valve only needs 210 milliamps. So I ended up buying this for $15. And I was able to control that PVC 2-inch solenoid valve with this 120 volt to 24 volt AC at 500 milliamp rated. This adapter rated at this could drive that valve. And then I have another example here. I'll give you a little circuit, nothing complex, okay? And I want you to determine the average power or the true power absorbed by this device here. And this device is comprised of a resistor plus a 2 ohm resistor and a J2 ohm inductive reactance. Well, that could be a motor. I mean, that very well could be a small AC motor, or it could be the model of the resistance maybe of my solenoid valve. But I want to determine the average power absorbed by this load, this impedance. Well, there's my analysis. I went ahead and calculated the current. You have to think, what do you want to end up with? You draw the picture. Remember I told you to draw the picture. You write down what you have, you write what you need, and you look for an equation that has 2 out of the 3. Well, there's that equation. I didn't give you RMS values up here. If I gave you RMS values, you'd use another equation. You use this equation. I make the calculation. The power is 12.48 watts. We could have also analyzed the circuit a different way using the voltage divider rule. I could have got a voltage across that, and I could have used this formula for true power or average power just across the resistor. Why am I using just the resistor down here? Because I know there's no power here. It's the inductor. The power loss is just in the resistor. So I go ahead and I make that calculation, and I look, it's the same answer. It can easily be shown using Ohm's law that here's another equation for the true power, and Vmax squared divided by 2R, or the true or average power can be Imax squared divided by 2 times R. Okay, this R here is in the numerator. This R appears in the denominator now. You have to be careful. But you get the same answer. In the textbook, there's 2 other examples I want you just to look at, just to make sure you can calculate average or true power. And I'll show you these for those of you that have a different book. There's example 9.2. We wish to determine the average power absorbed by the impedance. Well, you know what? That's the one. Is that the one we just did? Yeah, that's the one we just did. And I worked it out for you. So let's look at example 9.3. It's this one right here. In the circuit shown there, we wish to determine both the total average power absorbed and the total average power supplied. True power absorbed and the true power supplied. You just have those equations written down and you go through the solution. And there's how the author comes up with the solution right there. You can go ahead and stop the video and just take a look at how they make that calculation there. They ended up with the average, the total average power absorbed, or the true power absorbed, is that 46.7 watts. And the average power supplied, it better be 46.7 watts also. And it is. Keeping in mind in that problem there that there's absolutely no power, average power, dissipated in that J minus J1 ohm inductor or capacitor in that problem because it's reactive. The only power absorbed is in these two resistors. The only power supplied obviously is right here. So you had to find the currents or the voltage, either one. There's many ways of working this out. You could find that voltage right there. So you just use your analysis that we did in previous chapter and find the voltage there. Or find the currents. And you use one of the equations I gave you. There's another example right there that's a nice example. Find the average power absorbed by each resistor in that circuit. And there's the answer right there. Finally, we might as well look at that example right there as well in the textbook. These are all examples I could throw on an exam. We'll just stop at 9.2 right there. And then there's the answers for that. This book is loaded. The books are loaded with examples here. The example 9.4, find that in your textbook. And there's the circuit. And then we just go through the analysis. These are simple analysis problems. There's nothing difficult here with these analysis problems. Take a look. There's the answer. The answer is 54 watts. 18 watts and 54 watts. So that includes this first lecture on the details of power. And what we covered was instantaneous power and average power, also known as true power. And that concludes this lecture.